Now, one more topic to discuss before we get into collisions, and that is the idea that an object can have angular momentum, even if that object isn't technically rotating in the way that we've come to think about rotation. And so I want to take a moment to talk about this. Let's imagine that you are standing in a field and you have your right hand and your left hand outstretched, okay? That's what you see in this image on the left-hand side. And let's say that three tennis balls are launched out of a cannon at a relatively safe speed. A, B, and C are the three different tennis balls. And they're each placed a distance d apart from each other. Now, each of the tennis balls is launched with the exact same velocity, and they all have the same mass. So we could say they all have the same linear momentum as they travel towards your body and your outstretched hands. Now, I want you to imagine what would happen as each tennis ball collides with you. When your right hand is outstretched and you catch tennis ball A, right? So for example, we'll just see tennis ball A hits your right hand, you're going to start to rotate essentially that way, right? Your body would probably rotate in that direction. And so even though the tennis ball A only had linear momentum, it caused you to rotate. And we're going to see that that's very important in a moment here. Now, if tennis ball B hits your body, right, this one's just going to bounce off the center essentially. Tennis ball B is not going to cause you to rotate. It's going to hit your body and bounce right off. Now, tennis ball C would hit your left hand and cause you to rotate in sort of this fashion, so the opposite direction. But again, it would cause rotation of your body. And so because tennis balls A and C have the capacity or the ability to cause you to rotate, they have angular momentum in this case. Now, I should mention that this is relative to the center of rotation of your body in this example, which we could represent by a point here, this point X, right? So if we say this is, or point Q really, this is just an X marks the middle of your body. Point Q is the center of rotation. Okay, now I want you to imagine what would happen if you took a step to the right. Right, and so what if instead of ball B hitting your chest, right, ball A hit your chest and ball B hit your left hand? Let's imagine you just shifted up one tennis ball length. Well, then ball A would just hit your chest and bounce off, and the ball B would hit your left hand and cause you to rotate. And so we see that depending on where you stand, some of the tennis balls have angular momentum and some don't because of their ability to cause you to rotate. And so angular momentum for objects traveling in a straight path, especially in a collision, is an arbitrarily defined idea. I want to make this point clear. It is not absolute. There is no absolute amount of angular momentum either of these objects have because they're all traveling in a straight line, and essentially their angular momentum is really dependent on what object you're looking at and where the center of rotation of that object is. So we can say that the angular momentum of a point mass, right, if you consider each of these tennis balls point masses, relative to some axis of rotation can be calculated as such. L, the angular momentum of that point mass, I'll say L for the point mass here, is going to be equal to, right, the linear momentum multiplied by D, the distance from the axis of rotation. Okay, and if the linear momentum of an object is its mass times velocity, then we can just write this as mass times velocity times d. And so that will help us calculate the angular momentum of a point particle when we're dealing with a collision, because when we deal with a collision, right, that particle having linear momentum could cause another object to rotate in that collision. And so this equation will help us calculate the angular momentum of objects that we may not really, most of the time consider to have angular momentum. Okay, now let's put this all together and look at an example problem of a collision involving the conservation of angular momentum.